Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Today, I would like to present about the introduction of the stabilizer during pitch up and pitch down. An aircraft stabilizer is an aerodynamic surface including movable flight control surface that provide the longitudinal and directional stability and control. Depending on the context, stabilizer may sometimes describe only the front part of the tail assembly. Stabilizer can feature fixed or adjustable structure on which movable control surfaces are hinged, or they can be fully movable surface such as a stabilizer. In the conventional aircraft configuration, stabilizer form an empennage position at the tail of the aircraft, with the vertical and horizontal stabilizer being distinct elements. Other tail arrangements such as V-tail configuration provide the combination of longitudinal for the pitch and directional for the yaw stabilization and control. Longitudinal stability and control may be obtained with other wing configurations, including canard, tandem wing, tailless aircraft. Some types of aircraft are stabilized with electronic flight control. In this case, fixed movable surface located anywhere along the aircraft may serve as active motion dampers or stabilizers. This is the example of the single type of tail that using the vertical and horizontal stabilizer. The conventional tail, the vertical is mounted exactly vertically and the horizontal stabilizer is directly mounted onto the empennage, that is the rear the fuselage. This is the most common vertical stabilizer configuration. For the T-tail, a T-tail has the horizontal stabilizer mounted at the top of vertical stabilizer. It is commonly seen on rear aircraft engine. T-tails are often incorporated on configurations with fuselage mounted engines to keep the horizontal stabilizer away from the engine exhaust plume. T-tail aircraft are more susceptible to pitch up at high angle of attack. This pitch up results from a reduction in the horizontal stabilizer lifting capability as it passes through the wake of the wing at moderate angle of attack. This also results in a deep stall condition. T-tails present structural challenges since load on the horizontal stabilizer must be transmitted through the vertical tail. And lastly, for the cruciform tail, the cruciform tail is arranged like a cross. The most common configuration has the horizontal stabilizer intersecting the vertical tails somewhere near the middle. And that's all for the introduction of the vertical stabilizer during pitch. And I would like to pass it to my friend. Thank you.
Assalamualaikum. My name is Muhammad Faiz and I will present about horizontal stabilizer. At the rear of the fuselage of most aircraft finds a horizontal stabilizer and an elevator. The stabilizer is a fixed wing section whose job is to provide stability for the aircraft to keep it flying straight. The horizontal stabilizer prevents up and down or pitching motion of the aircraft nose. The elevator is the small moving section at the rear of the stabilizer that is attached to the fixed section by hinges. Because the elevator moves, it varies the amount of force generated by the tail surface and is used to generate and control the pitching motion of the aircraft. There is an elevator attached to each side of the fuselage. The elevator works in pairs. When the right elevator goes up, the left elevator also goes up. The elevator is used to control the position of the nose of the aircraft and the angle of attack of the wing. Changing the inclination of the wings to the local flight path change the amount of lift which the wings generate. This in turn causes the aircraft to climb or dive. During takeoff, the elevators are used to bring the nose of the aircraft up to begin the climb out. During a bank turn, elevator's inputs can increase the lift and cause a tighter turn. That is which elevator performance is so important for fighter aircraft. The elevators works by changing the effective shape of the airfoil of the horizontal stabilizer, changing the angle of deflection. At the rear of an airfoil, change the amount of lift generated by the foil. With greater downward deflection of the trailing edge, lift increase. With greater upward deflection of the trailing edge, lift decreases and can even become negative. The lift force is applied at the center of pressure of the horizontal stabilizer, which is some distance from the aircraft center of gravity. This creates a torque on the aircraft and aircraft rotates about its center of gravity. The pilot can use this ability to make the airplane look, or since many pilot aircraft look naturally, the deflection can be used to trim or balance the aircraft, thus preventing a loop. If the pilot reverses the elevator deflection to down, the aircraft pitches its opposition
Assalamualaikum,
direction.
my name is Muhammad Sabit and I will be explaining about aircraft motion. In flight, any aircraft will rotate about its center of gravity, a point which the average location of the mass of the aircraft. We can define a three-dimensional coordinate system through the center of gravity with each axis of this coordinate system perpendicular to the other two axes. We can then define the orientation of the aircraft by the amount of rotation of the parts of the aircraft along this principal axis. The pitch axis is perpendicular to the aircraft centerline and lies in the plane of the wings. A pitch motion is an up or down movement of the nose of the aircraft. The pitching motion is being caused by the deflection of the elevator of this aircraft. The elevator is a hinge section at the rear of the horizontal stabilizer. There is usually an elevator on each side of the vertical stabilizer. The elevators work in pairs. When the right elevator goes up, the left elevator also goes up. As, as described on the shape effect slide, changing the angle of deflection at the rear of an airfoil changes the amount of lift generated by the airfoil. With greater downward deflection, lift increases in the upward direction. With greater upward deflection, lift increases in the downward direction. The lift generated by the elevator acts through the center of pressure of the elevator and horizontal stabilizer and is located at some distance from the center of gravity of the aircraft. The change in lift is created by deflecting the elevator, then generates a torque about the center of gravity, which causes the airplane to rotate. The pilot can use this ability to make the airplane loop, or since many aircraft loop naturally, the deflection can be used to trim or balance the aircraft, thus preventing a loop. On many aircraft, the horizontal stabilizer and elevator create a symmetric airfoil like the one shown. This produces no lift when the elevator is aligned with the stabilizer and allows the combination to produce either positive or negative lift, depending on the deflection of the elevator. On many, on many fighter planes, in order to meet their high maneuvering requirements, the stabilizer and elevator are combined into one large moving surface called a stabilator. The change in force is created by changing the inclination of the entire surface, not by changing its effective shape.
Assalamualaikum. My name is Khairul Hafiz bin Baharuddin, and I would like to make a conclusion of what our members have done. In aerodynamics, pitch up is a severe form of stall in an aircraft. It is directly related to inherent properties of all swept wings. Pitch up problems were first noticed on a high-speed test aircraft with swept wings. It was a common problem on the Douglas skyrocket, which was used extensively to test the problem. Before pitch up phenomenon was discovered, it plagued all early swept-wing aircraft. In the F-100 Super Sabre even got its own name, the Sabre Dance. In aircraft with high-mounted tailplanes like 101 Voodoo, recovery was especially difficult because the tailplane was placed directly in the wake during the pitch up, causing deep stall. Deployment of the braking parachute at considerable height above the ground were essentially for a chance in recovery. The wingtips of the swept wing operate a higher local lift coefficient than the inboard section of the wing, so the wingtip are more heavily loaded than the inboard section. In addition, swept wings tend to generate span-wise flow on the boundary layer. This problem is primarily seen at low speed. The combination of these factors means a high angle of attack, especially at low speed. The wingtip stall before the rest of the wing. Since the wingtip of swept wings are by definition further than the wing roots, wingtip stall result in a considerable forward shift of the center of pressure relative to the center of mass. The result is a rapid upwards pitch in the aircraft nose. If the tail planes of an aircraft are caught in the resultant wake coming off the wings, they may have not enough authority to pick up a horizontal flight, and the aircraft will continue to nose up higher and higher. In some circumstances, the aircraft can actually tumble end over end, sometimes at supersonic speed, and the recovery may be difficult or impossible. Sometimes an intentional rapid pitch up by the pilot, such as high speed hairpin turn in a fighter jet, will cause the aircraft to become uncontrollable and it may begin to tumble. As the primary causes of the pitch up problem are due to span-wise flow and more loading of the tips, measures to address this issue can eliminate the problem. In early design, these were typically add-ons to otherwise conventional wing platform, but in modern design, this is a part of overall wing design and normally controlled by the existing high lift devices. A common solution to the problem of span-wise flow is the use of the wing fence or related dogtooth notch at the leading edge of the wing. This disrupts the flow and redirects it rearward, while also causing the build-up of stagnant air inward to lower the stall point. This doesn't have effect on the overall airflow on the wing, and is generally not used where the swept is mild. To address the problem with loading, a wider variety of techniques has been used, including dedicated slats or flaps, the use of washout or automatic controls of the aileron. An unusual solution tried on an XF-91 Thunderceptor prototype fighter was to give the wingtip the wider chord than the wing roots. The idea was to increase wingtip and cause the wing root to stall first. A commonly used solution to pitch up in modern combat aircraft is to use a controlled canard. Another modern solution to pitch up the use of slats, where slats are standard. They increase the wing camber and increase maximum lift coefficient. Pitch up is also possible in aircraft with forward swept wing, as used with the Grumman X-29. With forward swept wing span-wise flow is involved, causing the wing root to stall before the wingtip. The reduction for lift at wing root causes nose-up momentum and ultimately will lead to pitch up. And that's for all from me. Thank you.